feel like I'm forgetting something.
So it wasn't recording earlier?
When?
It wasn't recording like
Just now? No.
I was like doing this.
Oh, no, it wasn't on yet. It wasn't on. I didn't see you doing that. All right, let's get started here. I did offer a bonus question. Does anybody have that? Anyone else have that? I'll take it now, but not later. Did you say you did? So I might cover this. Yeah, I might cover this if we have some time at the end of class today. But we have an exam on Tuesday, right? So, let's make sure we can get through this material. You're kind of lucky because your exam's on Tuesday and we're going to finish the material that's going to be on the exam today. Where my Monday, Wednesday class, on Monday they finished their material and then they had the test immediately on Wednesday. So you're the lucky class. Just worked out that one. So I'm going to email them and tell them they can watch this video if they want to see what we're going to do Monday. But whatever. Okay. All right. So last time I gave this problem as a bonus. And I will get to it if I can. We're ready to start type 2 improper integrals. So for type 1, they were called infinite integrands. Or sorry, no. I just said that completely backwards. Type 1 was limits at infinity. And your limits of integration are the numbers on top, A and B, right? Top and bottom. If either one of those are infinite, right? Infinity or negative infinity, then we have a type 1. All right, so what's happening is we're looking at the area under a curve going in one direction or the other forever, right? And we've seen, especially if you did your homework, that sometimes you get convergence, sometimes you get divergence. It just depends. Now, the second type, we are not looking at going out in each direction forever. What we're trying to address is the possibility that our function may have an I can't say it right now, asymptote. All right, so remember vertical asymptotes? Vertical asymptotes are places where your function starts to take off to infinity or perhaps goes down to negative infinity. And usually in college algebra, we represented that with a vertical dotted line. And the important point was that that point is not in the domain of the function because it causes division by 0 in the function. So we want to look at, what if we ever get an integral where we have a discontinuity, an infinite or a vertical asymptote somewhere within the place we're trying to integrate. So here's a picture, all right? So let's say that we have a function and we're trying to integrate, here you can see 2 and 5, but let's just say that's A and that's B. What if we have this vertical asymptote occurring at A, right? So when we plug A into the function, we get division by 0. We know we would have a vertical asymptote there, right? So this area, over here we get, this is no problem. We have area, it's going to stop somewhere. But in here, we start to get area. And if we were to zoom in here, we know that the function just keeps getting closer and closer. And there's always some space between the vertical asymptote and our function, right? So there's always some area in there. So it's almost like what we did last class, where we're going this way forever, right? And we have area in there the whole time. It's the same thing, but now it's like a vertical instead of a horizontal, all right? So we should be able to address this somehow. So we can have a vertical asymptote occurring on the left endpoint of our interval. We could have a vertical asymptote occurring at the right endpoint. So let's say that this is A and this is B. So what if B is where we have the problem, right? Then what do we do? Or, third possibility, what if we're going from A to B and we have a vertical asymptote somewhere in between? right? So maybe at A it's fine, maybe at B it's fine, but in the middle we have a major problem, all right? Do y'all understand visually what's happening here? So let me show you one of the most common mistakes that I would see on a problem like this. Just watch this. What if I wanted to do an integral from -1 to 2 of 1 over x squared dx? Okay? So according to what we've said, what we've learned about definite integrals, we would first find the antiderivative of that, right? Okay, so the antiderivative of that is -1 over x. And I think we've done that enough that that's okay. And we'd evaluate that from -1 to 2, right? So then you plug in 2. We plug in 2 here, we get -1/2. And if we plug in -1, we get what? 1? And so what is this telling me my area is? -1/2 minus 1? -3/2, right? That just can't be right. Because what does this function look like? You remember what that function looks like? That's that volcano one, right? Like this. And we were integrating from -1 to 2. So we were trying to find this area here and all that, right? There's no way the area is -3/2, right? So something is wrong. And what's wrong is when we did the problem, we did not recognize that this is a type 2 improper integral. We didn't recognize that when we looked at our interval from -1 to 2 on the number line, we didn't realize that at 0, we have a discontinuity. At 0, our function is undefined, right? So that's what today is about. We have to be careful not to just start showing off, yeah, we know how to do it, and not realize that, oops, we had a discontinuity in there somewhere, all right? So we have to pay attention to that. And that's especially dangerous because when you have like infinity or like negative infinity or infinity here, I think that automatically you know you're going to have to do what we did last class, right? But if you don't, then you have to remember that you also have to check to make sure that you don't have this happening, right? So it's less obvious, this type 2, all right? All right, so let's do a problem. Oh, I should talk about how we're going to do them, sorry. How are we going to address it? Because that answer I just put up there is wrong. So how would we do that? Well, yes, uh-huh.
If the graph is on the positive side, you said it cannot be a negative area.
Yeah, remember there was properties of integrals that we had talked about before? There was like 8 or 9 properties that I put up here, and one of them said that if the function was always above the x-axis, then the area had to be positive, so that answer just doesn't make sense. All right, in all of the cases above are considered to be type 2 infinite integrands. Now they call it infinite integrands because it's the integrand. It's the thing, the function itself is called, the function is the integrand. This function right here, that's the integrand. So what's happening is that somewhere in our interval, our integrand is becoming infinite. That's the vertical asymptote. So that's why we call it infinite integrands for type 2. Blah, 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 that's what I say right there. So how do we do it? Well, let's take a look at this case right here. Let's say that we have a function and it's continuous on the half-open interval AB. So notice that there's a parenthesis on the B and a bracket on the A. That's just saying that you have a function where, yes, you can plug A into the function. So this left endpoint, A, it's all good, right? But at B over here, you cannot plug this point into the function because you get division by 0, right? So what if you're continuous on AB, right? You can call this a half-open or half-closed interval. It's the same thing. And discontinuous at B, so discontinuous at the right endpoint. Then here's how we do it. And this is going to look very similar to what we did before. See, B is where we have the problem, right? B is where we have the problem. So what we're going to do is we're going to take a limit again. We're going to replace the B with T, and we're going to let T approach B. Not approach infinity, approach B. So what we want to do is say, hey, what happens if we start trying to find the area and we start moving this right endpoint really close to B without actually getting there. And notice also this little negative sign. What does that little negative sign mean on a limit? From the left side. So does it make sense that we're approaching from the left side here? If we're looking from A to B, and B is where we have the problem, then we have to approach B from this side. All right, so it's going to be we call this a single-sided limit. You're only approaching it from one direction. All right? That's how we'll do it. You'll see this in practice when we do a problem, okay? Now, if we approach B from the left side, of course this limit must exist and yield a finite number. Okay, so we must, once we take that limit, if we get a finite number, then we say it converges. Otherwise it diverges. Now, same idea, but this time let's let us have a problem at the left endpoint, at A. Then we're going to do the same setup, except because A is the problem, we're going to replace A with T, and we are going to let T approach A this time from the right, because our interval goes from A to B, right? So we're going to approach the A from the right. And then we take that limit, and hopefully it exists, and hopefully it's a finite number, and then we have an answer and it converges. Yes? Okay. This is me just saying if the limit exists, it's convergent. If it doesn't, it's divergent. All right, so what if you have a discontinuity in the middle? What if, this is A, this is B, and you have a discontinuity somewhere in between at C? What do you think we'll do? Well, the limit may or may not exist. The function doesn't exist at C, right? Yeah, we're going to basically break it into two integrals. All right, so what we'll do is we will go, if we're trying to go from A to B, and there's a discontinuity somewhere in between them, somewhere in between A and B, let's say at C, then we'll first go from A to C, and then we'll go from C to B. Now, when we go from A to C and we do that integral, we'll have to replace C with T, and then take the limit as T approaches C from which side? From the left side. But when we do this integral from C to B, we'll have to replace C with T and approach T from the right-hand side. So it's going to be, this problem right here is actually two problems, right? Just like when we had negative infinity to infinity, we broke it into two problems. When we have this, we have to break it into two problems. All right, let's take a look at the first example. Now, this is not the problem I put on the board earlier, right? Earlier I put negative 1 to 2, or what did I put? Whatever. Didn't I? 1 over x squared. It was 1 over x squared, but was it negative 1 to 2, right? Here we're going from 0 to 1, all right? 0 to 1.
So do you have these notes online?
Oh yeah, they're all online. Yep, they're in the Canvas, Canvas under Files, under Notes. Yep. Yeah, anything that I ever show y'all up here, all of this stuff has been on Canvas since day one.
I thought I printed everything. Maybe I missed that one.
This would be 6.6, improper integrals, or 6-6. All right, can y'all see that okay?
Yeah.
Make it a little bit bigger. All right. So we take a look at this, and first let's look at the integrand, f of x. It's 1 over x squared, right? Where do we have a discontinuity? Where do we have a problem? Okay, so this is discontinuous at x equals 0. So now we ask ourselves, is x equals 0 in our interval? Yes, it is. We're going from 0 to 1, right? But notice what the question I'm asking myself is it anywhere in the interval, including the endpoints? It is, right? And that's what you want to kind of get into a habit of doing, is making sure you're checking, like, is this discontinuity anywhere in that interval? Here it's at the left endpoint. So it's discontinuous at 0. So now this is just stuff I like to do to kind of help me get things set up. I like to draw a number line. I like to actually draw my interval 0. I like to draw the other end 1, right? That's where I'm trying to find the area between here and here. And this is where I'm looking, right? And this is where I have the discontinuity, right? At 0. So that means I'm going to have to approach 0 from this direction, from the right, yes? All right, so now let's set this up. The integral from 0 to 1 of 1 over x squared dx must equal the limit, or will equal the limit as t approaches what? Yeah, the discontinuity from the right side. How do I do that? Little plus sign up here. Of the integral t here and 1 here, right? So I'm replacing the 0 with t. I'm approaching that 0 from the right. And then it's just the integrand. Nothing's changed there. So any questions with that?
So is there an easy way to remember which one you're going to replace with t?
Yes. Which one? Where do you have the problem? Where's the problem occurring? At 1 or at 0? That's the one we replace, right?
What if there's no discontinuity?
Then we won't do this. Like if we were integrating from 1 to 10, right? If we were going from 1 to 10, I would have drawn a number line. Here's 1, here's 10. But look, 0's over here, right? I don't care then. I don't care about this then. So I just integrate it the way I normally integrate it. I'm only concerned if we have a problem within the interval we're integrating over.
You have to replace with t and a.
Nope. Nope. You just do what I did a second ago when I was showing you how you can make a mistake. You just do that because there's no problem.
If it's going to infinity and there's no discontinuity, then you have to replace with t, right?
If you're going to infinity, yes. You always have to replace infinity with the t and take a limit. If one of these are an infinite, then you have to do a limit. All right, now, leave this here. Now this is still a limit. T is approaching 0 from the right. And we have, let's go ahead and take the antiderivative, right? So if we take the antiderivative, we get negative 1 over x. And we're going to evaluate this t in 1, right? Yeah, I'll get rid of this. Now we plug in, right? Still have a limit out here. T is approaching 0 from the right. And we're going to do two things being subtracted here. So first we plug in 1, right? When we plug in 1 for x, we get negative 1 over 1. And when we replace x with t, we get negative 1 over t. And at this point, we can actually take the limit. So there's no t here, right? So that's just negative 1. So don't have to worry about that. Over here, we're asking ourselves, what happens to this right here, this expression, if I let t approach 0? Well, t goes to 0, right? 1 over 0, 1 over something that's getting smaller, that ratio gets bigger, right? Now, it might get big negative or it might get big positive, but who cares? It's getting huge, isn't it? This right here is becoming infinite. Now, you could actually figure out whether or not it's positive or negative infinity by just looking. Like the numerator, let's say the numerator is negative 1, right? Your denominator is approaching 0, but it's approaching 0 from the right, yes? So those numbers are getting very, very small, but they're always positive. So you have a negative number over a very small positive number that makes a very big negative number, right? So we know that this right here is approaching negative infinity. And that's it. I mean, we are done at this point because it's not converging to a number, right? That's not going to a number. It's diverging. It's going to infinity. So this thing is divergent. That makes sense? Yes? This right here would make it positive infinity, right? Yeah. Either way, it's blowing up. It's not converging to a number, right? Okay, so if I wanted to say what this was equal to, right? If I wanted to just finish it off, then I would have to pay attention to signs. So this would be negative 1, right? I'll just put it here. It would be -1 and then minus negative infinity. So this would actually be coming, this whole thing is going, approaching positive infinity. And that at least should settle in your mind a little bit better because, you know, this is what the graph looked like. And we were only looking from 0 to 1, right? We were only looking from 0 to 1. So we were looking at this area here, but that kept on going up forever, right? And it turns out that that's an infinite area. And it's positive, right? It's above the x-axis. Yeah? There's something kind of strange with this. I've always thought that this is somewhat strange. Compare what we just got. Let's just say diverges, okay? This is it, diverges. Okay, so this diverges. Now, compare this integral from 0 to 1 of 1 over x squared dx to the integral from 1 to infinity of 1 over x squared dx. So same function, right? Here we're looking at the area between 0 and 1. Here we're looking at the area from 1 to infinity. What's the answer to this one? Convergent or divergent? It's convergent. That was the bonus question also, right? If we look at something like this, if we're going from 1 to infinity, and that number right there, we call it p. If that number is bigger than 1, it converges. So it's kind of strange because it's like the area out to the right forever is finite, but the area between 0 and 1 is infinite. So it's like opposite, right? It's like opposite. Yeah? It's just the way it is. It's just the nature of it, okay? I wonder if that would also work with this. Check this out. Let's do a different example. All I'm going to do is I'm going to scratch that and just make it 1 over x instead. Okay? Now, do you remember what 1 over x did when we went from 1 to infinity? Last class? From 1 to infinity of 1 over x? That diverged, right? I wonder if from 0 to 1 it's going to converge. All right. So first, limit t approaches 0 from the right. The setup is exactly the same on this one because we have a discontinuity at 0, don't we? So same exact thing. I have an integral from t to 1 of 1 over x dx. Is that okay that I didn't draw the number line and do all that? It's the same exact issue we're having at 0. Now, this becomes the limit as t approaches 0 from the right of the antiderivative of that is what? ln of the absolute value of x, right? And I'm going to evaluate that t here and 1 here. And then that equals still a limit. T is approaching 0 from the right. And two things here, subtracted. So we plug in 1 first. That's natural log of 1, right? I'll just put it here. We know that's 0, right? But I'll put natural log of 1. I also didn't use the absolute value because 1 is a positive number, so absolute value of 1 is still 1. And then plug in t here, natural log of absolute value of t. I actually don't need the absolute value, again, because t is positive. Why do we know t is positive? Because we're approaching 0 from the right, so it's positive. So I don't need the absolute value, but I'm going to keep it there. Now, this is 0, right? 0 minus this. We're going to replace t with 0, or we're going to take the limit as t goes to 0. So what does the natural log function do as you approach 0 from the right? This goes back to, again, last class, we have to know what the natural log function looks like, right? So what happens on the natural log function as you approach 0 from the right-hand side? Where does it go? It takes off to negative infinity, right? So this heads to negative infinity. In the limit, it heads to negative infinity. And so this whole thing is headed to infinity, which means it diverges. Okay? So 1 over x, if you graph that function, we learned last class that this area over here is divergent, right? And we just learned right now that this area here is also divergent. It's infinite. But 1 over x squared was different, right? 1 over x squared, this converged, this diverged. Maybe we should do one more. Let me see what my other examples are. Hold on. Nah, we won't do that one yet. Let's do one more. How about integral 0 to 1 of 1 over root x dx? Hey, and just for fun, can we go 0 to 4? Okay, good, we will. Just because we don't have to go, this doesn't always have to be 0 to 1, okay? It can be 0 to anything. We just need to check to see whether or not we have a discontinuity. So do you see we have a discontinuity? It's at 0 again. And so we're going to need to approach 0 from the right-hand side. So we do limit. T approaches 0 from the right of the integral t to 4. And then we're going to need to integrate this, right? This is x to the negative 1/2. It's 1 over root x. Yeah? I'm just getting ready for the power rule, right? So this is limit t approaches 0 from the right. The antiderivative of that is what? Two root x, or 2x to the 1/2. And we're going to be evaluating here t and 4. Oops. T is approaching 0 from the right. We're going to be plugging in two things. So let's plug in 4 first, 2 root 4. And then here we're going to have 2 root t. What are we getting here? This is what? That's just 4. 4 minus, now let t go to 0. It's just 0, right? It's just 0. See, we don't have division by 0 anymore. It's not the natural log like the last problem, so we don't have to look at that. It's just that goes to 0, no big deal. So what's happening here? It converges to 4. So if you graph 1 over root x, if you were to graph that, it would actually still look like this. It would look like this if you graphed it. I mean, it's different than 1 over x squared. It's different than 1 over x. But the area from 0 to 4 for this one, that area, forever up in there, is finite. And it all has to do with how rapidly this thing is changing. And all these functions are just a little bit different because the powers on x are a little bit different. And so that has an impact on whether or not it has a finite area or an infinite area. Yes?
What did you say, 2 radical t is equal to 0?
Because I'm taking the limit as t goes to 0. So I'm just replacing t with 0, and that's all gone. Yes?
Just real quick.
Yeah.
So in this one, you actually replace t with 0,
Mm-hmm.
and you let it be 0. In the other ones, you replace t with 0, and you let that be infinity or negative infinity.
I didn't let it be negative infinity or infinity. When I plugged in, when I replaced, that's what that expression was doing. So in the first example, if you look back, I had 1 over t. Second example, I had natural log of absolute value of t. Those are the two things that we had. When I take the limit and I let x approach 0 here, this approaches negative infinity. Because that gets small, the ratio gets big. Okay? This one, natural log of 0 is undefined, but as you approach 0, we have to look at the graph and we can see that that graph dives down. This, if I let that approach 0, then it's just going to become very small, right? And the square root of something very small is still very small, and 2 times very small is very small, so it's approaching 0, right? So I have 4 minus a number that's approaching 0. This whole thing is approaching 4. So there's no weirdness happening here. We don't have something like this or this. That make sense? Okay. Now let's do the next example I have in the notes.
Do you use notice graphs or?
The natural log function and these power functions, yes.
How long have you been teaching for again?
This is my first semester. Long enough. Long enough. Okay, take a look at this one. This one's a little different. 1 over the square root of 2 minus x. We're integrating from 0 to 2. So if we look at our integrand, f of x equals 1 over square root of 2 minus x, we need to be very careful that the interval we're looking at from 0 to 2, that nothing in here causes a problem. So can I plug 0 into this? Sure, 2 minus 0, that's square root of 2, big deal. If I plug in a number in here like 1 would work, right? And the only number that causes a problem is 2, because 2 minus 2 is 0, and then you get division by 0. So this is a problem, right? So we're going to need to approach that number from the left-hand side, aren't we? And it's the upper limit of integration is where we have the issue, right? Up here. So that's going to be the part that's replaced with t. And we set up the limit. Yes?
So then we do that for every problem, like to check basically where we're going.
Yeah, yeah, you should. I mean, when you look back on it now, you remember when we were doing rational functions, partial fractions, and then we'd like factor the denominator out? If we had a definite integral with numbers now, we would have to make sure that none of those factors were ever 0. Now, I'm not going to throw that at you on the test. I mean, it's going to be something similar to like this or anything I do today. But yes, in theory, you should always check that you don't have any discontinuities within your interval of integration. And this is what we do to do that. All right, let's do this. This right here becomes the limit. T's approaching what? 2 from which side? Left side. Okay. On that, let me just state something real quick. On that last problem, do you remember we had 2 square root of t, and we were approaching, what were we approaching here? 0 from which side? Right. The right side. I haven't stressed to you how important it is that we're coming in from the right side of 0. Because if you have 0 here, and I say, hey, approach 0, and I don't tell you which side, you could come in from this side, right? And that would be a negative number. And if you try and put a negative in there, it's undefined. Do you agree? But because we were approaching 0 from the right-hand side, those were always little positive numbers we were plugging in. And if you plug a positive into a root, you're good to go. So that one-sided limit is actually important in some of the little aspects of what's happening in this, in the limit. It might be a little more apparent in this one. We'll see. Okay, so now limit, now integral, where to where? 0 to t, right? And then we have this thing, 1 over the square root of 2 minus x dx. And now we get to integrate that, right? How are you going to integrate this? How are you going to do this integral? Basic U-substitution. Basic U-substitution. We would do something like u is 2 minus x, du is negative dx because we have a negative in front of the x. And we don't have a negative dx, so we change that minus, make that plus. Rewrite the integral as negative on the outside, 1 over root u du, right? And the antiderivative of that would be, well, this is u to the negative 1/2. So the antiderivative of that is 2u to the half, but yet a negative out there. So negative 2u to the half root u. Okay, so I'm going through that fast because I'm expecting that, yes, you could do all that. And then what was u? 2 minus x, right? So that's the antiderivative of this. So that goes here now. Limit t approaches 2 from the left, and we have the antiderivative, which is negative 2 root 2 minus x. We're evaluating from 0 to t. It's looking pretty convergent to me. Let's see here. Limit t approaches 2 from the left. And now I have two things that I'm going to put in here. So first we replace the x with t. So negative 2 root 2 minus t. Then we replace the x with 0. Negative 2 root 2 minus 0. Bless you. Let it go, man. Let it go. All right. This right here is just negative 2 root 2, right? And then there's a negative out front. So how about just putting here plus 2 root 2? That's what that is, right? And then how about that first one right here? When I let t approach 2 from the left. Now, I do want to point it out in this one. We're approaching 2, right? From the left-hand side, which means these numbers are really close to 2, but not quite 2. So things like 1.999 would be an example of a number that's approaching 2 from the left. If I take 2 and subtract like 1.999, it's going to be a very, very small number, isn't it? The important thing is I can't come in from this side. You'll see why I can't come in from this side? Because then it would be bigger than 2. If I try and plug that in there, 2 minus a number that's bigger than 2, it's going to give you a negative number. And you can't take a root of a negative number. So the one-side limit is important. But it's so subtle that we can forget about it and it's not going to cause a problem. All right, so we're approaching here. So did everyone agree that this is approaching 0? Yep. That's approaching 0, and then times who cares because it's going to 0. So that's gone. And so our answer is 2 root 2. So we are convergent. The area between this function and the x-axis on the interval 0, 2 converges to 2 root 2. So another convergent area. And this is the function. If you graphed it from 0 to 2, this is the graph of that function. So we found this area right here all the way up forever and ever, amen. All right? And that's what it goes to. Oh. Now we got something a little more interesting. If I take these limits of integration off the table here, okay? If I just give you this integral right there, what are you thinking? What are you thinking? Partial fractions, maybe? Yeah? That's what I'm thinking too. So I think this was kind of the question that was posed a second ago. Do we have to address this? We do now. We actually have to consider for this integral, like, is there a problem in there? Do we have an issue, right? Okay, so let me check that. Let's take a look at the integrand. The integrand is f of x is 1 over x squared minus 4x. So let me factor the bottom. Pull an x out, we get x minus 4, like that. And let's take a look at the interval that we're integrating over. We're going from 1 to 4, right? So we're looking in here. Do any of these numbers cause problems at 4, right? So what we're doing is we're looking at the denominator here and asking ourselves, where do we have 0 down here? So 0 would have been a problem, right? But it's not in our interval, so we don't need to worry about it. 4 will make that 0, and that is in our interval. So we're going to have to talk about going and approaching 4 from the left-hand side when we do this.
Why 0 is included again?
Why is 0 not included? This is where I'm looking, right? Between here and here, where's 0?
I know, but why is it not? Why is it only 1 to 4? Oh.
It's all right, it's Monday, man. We're approaching 4 from the left, right? And the integral, we're replacing the 4 with t. And then we still have to integrate this. I'm going to go ahead and factor it now. I mean, it doesn't matter. I can do it now. I'll do it later. Okay? The next step is to find the antiderivative, right? So I think this is where we're going to need to step off to the side, do some scratch work, do all the work, partial fractions, do all that, and come back, put that answer in there. All right. So this is my scratch work on the side. I'm just going to look at this integral. I'm looking at the indefinite integral right now. Okay? That way I can slap the answer in here. So to do this, we're going to recognize that we have two distinct linear factors. Because we have two distinct linear factors, I can rewrite that as what? A over x plus b over x minus 4. And then you clear the fractions, and you get a times x minus 4, and then plus b times x. So that's clearing our fractions. And then we could actually do the shortcut on this one. So I'm going to do the shortcut. I'm going to let x be 0. Why? It's going to kill this one, right? So if I let x be 0, this equation becomes 1 equals 0 minus 4, negative 4, negative 4a. So that means a is negative 1/4. So I know what a is. And how could I figure out what b is? Let x be positive 4, because that'll kill that off. So if I do that, my equation becomes 1 equals 4x, right? No, 4b. And that means b is 1/4. Right? Okay. I think I'm ready to go to the next step over here. So we have this equals the limit as t approaches 4 from the left of the antiderivative. Now I better put this antiderivative in parentheses. It's going to be, oh crap, I never got the antiderivative. Sorry. This integral now up here becomes what? Sorry. Negative 1/4 over x, and then plus 1/4 over x minus 4 dx. Right, so that was just me using partial fractions to get it to here. Now, can you integrate each of these? Yes? Yeah, let me put it, I think I'm going to slap the answer right above this, okay? Right in here. This equals, negative 1/4 comes out, right? So negative 1/4, and then the antiderivative of 1 over x is natural log absolute value of x. Here, positive 1/4 comes out, and then natural log of x minus 4. Then plus c, but we won't need the plus c over here, right? So we have negative 1/4 natural log x plus 1/4 natural log of x minus 4. Absolute values on those. Evaluating 1 to t? 1 to t. How are y'all feeling about this? I mean, we're throwing a couple of more layers onto this, but it's not like it's not like it's a brand new thing here, right? We're just doing a limit.
It's just the cheese.
Yeah, exactly. It's the lasagna, right? Was this the class we were doing lasagna? This is that doing a little sprinkle of oregano on top, maybe? I told my other class about the lasagna. They didn't seem to get it. All right, so I have two things now, right? I've got to plug in something here and something here. This might look pretty ugly when we're done. Let's see. I'm like tempted to use properties of logs and put these together, but I'm not going to. I'm just going to let them stay the way they are. Right? I mean, I could do that, but nah, it's going to cause more problems. Negative 1/4 natural log of t plus 1/4 natural log of t minus 4. That's what happens when I plug t in for x, right? And now let's plug 1 in for x. So negative 1/4 natural log of 1 plus 1/4 natural log of, you can see how important it is that we have an absolute value here. 1 minus 4 is negative 3, but it's in an absolute value, so that's still going to be okay. I think we should let t go to 4 now. This is a number and this is a number, right? These are just numbers, so I'm not worried about that. Natural log of 4 is a number, right? No big deal. So that's a number. This is the last piece right here. If this works out, we're good. Replace t with 4. You get 0 here. And natural log of 0 is undefined, but we're approaching 0, right? We're approaching 0. And are we approaching 0 from the correct side? Well, the absolute value means that this is positive no matter what, right? Yeah. So the inside's approaching 0, but it's a positive number, so we're coming in from the right-hand side. Negative infinity. Negative infinity. All that to say that this diverges. It diverges.
So you're saying that like if one little section is negative infinity, there's nothing that will get rid of that infinity, right? So yeah.
I'm going to say yes and no. Because if this would have also been infinity, then you would have had infinity minus infinity, and that is an indeterminate form. So we would have had to have done something to figure out what's going on. So if one of them goes to infinity, that's not enough. You have to make sure that when you look at the whole thing, you don't have any indeterminate forms. This right here is going to a number, right? That right there? Plus negative infinity minus a number plus a number, right? And these are actual finite numbers. So we have one term going to negative infinity. That means the whole thing's done, all right? That diverges. Wonder if I graphed this one. Oh, there it is. So there's the graph of that function between 1 and 4 only. And hey, check it out. This graph is below the x-axis. And so it kind of makes sense that we got negative infinity. It's like a negative area.
On the test,
yes.
whenever we find out that it's divergent, do you want us to finish it out and show you?
You can just get to here and then you can say divergent. Yeah. Or you could put negative infinity and box it. So do you see that on the test I could give you an improper integral of type 2 and still require that you do partial fractions? So do you see how the test can become like 5 problems pretty easily? Like this one right here. Like we have to deal with whatever's going on, but we also have to deal with the integral. We actually have to be able to integrate it. So what's that phrase, killed like 2 birds with 1 stone, right? This is like 8 birds with 1 stone. You kill like 8 birds. Make sure you can take limits. Make sure you remember indeterminate forms from Cal 1. Make sure you can do partial fraction decomposition. Make sure that you, right? All this stuff. Let me remind you that I'm the messenger. I've told you this before. Let me remind you again. All right, here we go. First thing I'm going to do is see if we have any problems. All right, so when we look at this, the function I'm looking at is x over the cube root, right? Cube root of x minus 4. And I'm integrating, bless you, I'm integrating on the interval 3 to 5. And do I have any issues? At 4, right? Because at 4 you get 4 minus 4 at 0, can't have division by 0. Now we have a cube root here. That's actually very important in this problem because if this was a square root, then 3 wouldn't work, right? Actually, a bunch of stuff wouldn't work because you would have like 3 minus 4, that'd be -1. You can't take a square root of a negative number, but because it's a cube root, it's okay to have a negative under the root. We just can't have a 0 down there or else we have division by 0. Yes? So the only problem we have here is at 4. Now 4 is not one of our limits of integration, but it's in our interval. So this is going to be the one where we have to break it up into 2 separate integrals. We cannot overlook that 4 though. We can't just be like, oh, we'll go from 3 to 5 and just kind of skip the 4. We have to see that it's there. So this is now going to become, we're going to turn that integral into the integral from 3 to 4. Plus the integral from 4 to 5. And the good news is that we only have to find the antiderivative once, right? Because these are the same integrands. So finding the antiderivative will be the same. But each of those problems, right, each of these is its own limit, right? We have to do a limit for this one, and we have to do it for this one. And this one we're replacing the what with what? The 4 with t, right? And we're going to let t, well, let me do it. This one's going to be limit. We're going to go t approaches what? 4 from which side? Okay, left, because the integral that goes from 3 to 4, we're approaching 4 from the left, right? And that's going to be the integral 3 to t of x over cube root of x minus 4 dx. Then plus the next one is another limit, right? Now, do we want to reuse t? Or I'm going to use r. I think I used s last class, but I'm going to use r this time. Why not? Why not, right? R goes to 4 from which side? Right side. And that's because, well, we're going from 4 to 5, right? So we can only come into 4 from the right. So that's going to be approaching 4 from the right side. And then integral replacing the 4 with r and not replacing the 5. So on your test, I mean, I'm looking for all this notation. You know, I want to see your limits. I want to see everything written out. It's like an English paper, you know, proper punctuation. That's what I hope to see. Yes, sir. I don't need to see this, okay? If you can just look at that and know 4 is where the problem is, and as long as you address it correctly, I'm okay with that. You don't have to show it to me. This is just to help everyone see what's going on. Now, if you forget that there's a 4 and you just go 3 to 5 and completely miss it, then that's going to cost you more. All right, what should I do next? Let's actually find the antiderivative, right? Let's find the antiderivative. So I need to find the antiderivative of x over the cube root of x minus 4 dx. What? Voodoo? Is that what I heard? Voodoo? What else did I hear? U-sub? Trig sub? Y'all are naming all the techniques. Good job.
I mean, magic.
Magic,
No, this game, really, trig sub.
trig sub. So what do you want me to do? Do you want me to show you what it is? Okay. I mean, everyone's going to have an idea, hopefully, of what you would do. Just a basic U sub here, x minus 4. Okay. And then what's du? dx. Okay, so I'm going to be able to replace this right here with u. So that'll be cube root of u. This will be du, and then what do I replace x with? X is going to be u plus 4, right? Just solve that for x. And now when we rewrite the integral, we get integral, the x is u plus 4, and this is the key to the whole thing. The denominator is now cube root of u, right? Which is u to the 1/3. And now you have two terms on top, one on the bottom, instead of this thing. And this is du. So now what can you do? Split it up, all right? So this becomes u over u to the 1/3, which is u to the... Did I? No, that's 1/3. That's to the 1/3. You're okay with that? Yeah. You had me second guessing myself there. I was like, wait, was it? Yeah, no. Yeah, cube root means to the 1/3 power. So I did u over u to the 1/3 is u to the 2/3, and then 4 over u to the 1/3, I'm going to just write that as 4u to the negative 1/3 du. Antiderivative time? The antiderivative of u to the 2/3 is three-fifths u to the 5/3, right? But u is x minus 4. I'm going to go ahead and do it now. X minus 4 to the 5/3. So that's the antiderivative of that with u replaced with x minus 4. And then what do we get here? When we add 1 to that, we get 2/3, but then we have to multiply by the reciprocal, so 3/2. So plus, what's 4 times 3/2? I can't do it. 6. 6. And then x minus 4 to the 2/3. Plus c, but we don't need the c. Yes, sir?
Real quick, that 4 you can pull it out, right? That's what you did?
This 4?
No, over here, before you take the antiderivative, the u plus 4, you can take that 4 outside, right? Like,
Not right now you can't because it's one expression. If you split it into two integrals, you could. But right now you can't pull a 4 out because there's not a 4 here.
that was one of the mistakes I did in the last exam.
Yeah. Yeah, it has to be a common factor with each one. Now you could pull a 4 out here, make that a 1, but then that would have to become 1/4 u. Like you could pull a 4 that's not really here out. Yeah. All right, are we good up to here? This is our antiderivative? All right.